So welcome back. This is our 50th video about the factor elimination and the Jointree algorithm. And in this video, we're going to start discussing the Jointree. That is the traditional and most well-known name for factor elimination. So we can understand the Jointree as a way of constructing elimination trees. For me, a Jointree is also a type of a probabilistic graphical model. It's slightly different from the ones that we haven't seen before. So we can sort of split the graphical models in two classes. There are the graphical models that we haven't seen so far. There are the ones that are useful for modeling a problem. So they are very easy to state, for instance, the dependencies that we have in the problem into a graphical model that we can easily and make inference over. And there are other graphical methods that are more useful when we want to make inference over those structures. So it's common to convert one graphical model into another in order to answer the queries. So this is the case of the Jointrees. So we can understand as a graphical model. It is a graph. It has variables associated to the nodes. We have probability tables also associated to the clusters. So we see that it has the same components of the graphical models that we have seen before, but they are not good to model a problem, but they are very useful to answer queries. And the fact that we can store the partial computations into the nodes of the graphical model of the Jointree, it will be very useful in order to answer the multiple queries that we mentioned in the beginning of this lecture. So we're going to start this video by defining the Jointree, and later on we can see how we can propagate messages using this structure. So here we have the definition of a Jointree and also some properties that a Jointree must satisfy. So let's start with the definition. So the Jointree for a network G is a pair T and C where T is a tree. So it's important that the Jointree, it's not surprising, it is a tree, so we cannot find cycles in this structure. And C is a function that maps each node I in the tree into a label Ci, call it cluster. Okay, and the properties that a Jointree must satisfy are the following. So the cluster Ci is a set of nodes from G. Each factor in G must appear in some cluster Ci, and if a variable appears in two clusters, Ci and Cj, it must appear in every cluster Ck on the path connecting nodes I and j in the Jointree. This is also known as the Jointree property or the running intersection property. So here we have a Bayesian network and also a Jointree for this Bayesian network. And what we can see here first in the properties that is mentioning. So first, it is actually a tree, as we can see here, right? So there are no cycles in this structure. And when it mentioned the property, it says that the cluster Ci is a set of nodes from G. So when we look here, each node that we have here, like 1 and 2, they are the clusters. And these are the variables associated with cluster 1, and these are the variables associated with cluster 3, and so on. So this, when you say the clusters are a set of nodes in G, we need to decide which variables will be associated to each cluster. But when we do that, we have some issues because we must satisfy the other two properties, and the property is saying that each factor in G must appear in some cluster Ci. So we need to build those clusters in a way that we will be able to map the factors into the clusters. For instance, when we look at the node G here, this node G has a factor that mentions G and D and F, because this is going to be the probability of the G given its parents, there are D and F. So we need to find some node that has at least these three variables, and G, D, and F. So we can find it here is actually node 1. So we can associate this guy here into this node here. And of course, it must be also true for the remaining nodes in the Bayesian network. So we need to find a node that I can put a factor that just mentioned A. It can be here in node 5. One that mentions B and A can also fit here in node 5. One that mentions D, B, and A also fits here in node 5, and so on. Well, we have to find a place for every factor that we have. And the last property is this one here. It says that if a variable appears in two clusters, Ci and Cj, it must appear in every cluster Ck on the path connecting I and j. So one example is, for instance, variable A. So we can find variable A in this cluster. We can also find variable A in this cluster here. And we see that A also happens here. That's part of the path that goes from here to there. It also is mentioned here. And so it's present in the nodes 3 and 4. They are in the middle of the path between 5 and 2. And we can also define the separator for one edge ij as being the intersection between the clusters Ci and Cj. So we can see here in this example on the left here that we have, for instance, this cluster 1 and this cluster 3, and the intersection between these two clusters will be D, that is a common variable, and F, that's also a common variable. Here we have A, but it doesn't occur here. And also we have a G here in cluster 1 that doesn't occur in cluster 3. So the separator will be DF. Similarly, if we look here, we have ADF and ABD and intersections AD. So we see that A is common, D is also common, of course here, but here we have B that doesn't occur in node 3. In node 3 we also have F, doesn't occur in node 5. So the intersection is AD. And we have the notion of minimal and non-minimal joint tree. So this joint tree here on the left is minimal, and this one here on the right is not. And we know that one joint tree is minimal if we try to remove one of the variables in the clusters, it will cease to be a joint tree. And it will cease to be a joint tree because or we cannot map the factors from the network into the joint tree, or because we don't have the joint tree property anymore. So for instance, if we decide that we're going to remove like F from this node here, we don't have the joint tree property anymore because we have F in this node 6, and we have F in this node here that is 3, but we don't have F in the node 4, and the node 4 is part of the path between node 6 and 3. Another thing that can happen is that if we decide to remove one variable, for instance, we decide to remove like G from the node 1, we cannot map anymore. So I don't know if you remember, but in the previous slide we have a family that mentioned F, D, and G at the same time. So the factor that we had in that node cannot be mapped here anymore, and it will not be also be able to be mapped in any of the older nodes of the joint tree. So it will cease to be a joint tree because we cannot have the property of mapping factors into clusters. Okay, and in the right joint tree that we have here, it's a non-minimal joint tree, and we can actually remove the variable age from here, and from here. In this case, we will have exactly the same joint tree that we have on the left here. So we'll see later on that we can make some operations over the joint tree and make one joint tree that is non-minimal into a minimal joint tree and vice versa. So we'll see how we can operate over joint trees and change it. So we say that having no minimal joint trees, it doesn't make much sense because we know that the width of the joint tree is the size of the largest cluster minus 1, and if you have a non-minimal joint tree, it means that we have larger clusters, so the width will be larger as well. But what happened here is that frequently we are interested in using the joint tree to answer queries, and possibly the queries will be over some variables, and we don't have those variables in the cluster. And we need to add some more variables in the cluster in order to answer the queries that we are interested. So for instance, if we are interested in answering a query that mentions these 4 variables here, A, D, F, and H, we don't have in the original Jointree any clusters that involve these 4 variables. So what we do, we push the age through this path here and add it to this node. We see that this operation is valid, and we grow this node. Now we have a Jointree that has a larger width, but on the other hand, it can answer queries regarding this marginal here with these 4 variables. So this is the Jointree algorithm. So let's take a look at how we can operate and make inference using Jointrees. It's going to be a sequence of steps. So the first step is to construct a Jointree given a network, and we still don't know how to do this. For now, we're going to assume that we have this Jointree given as input, and we'll just follow the remainder of the steps. In the next lecture, we're going to discuss how we can build a Jointree from elimination order. So we can use all the risks that we have discussed in this lecture to build the elimination order, and from the elimination order to build a Jointree is one of the techniques that are used to construct Jointrees. But once we have a Jointree, and let's assume that we have this one, we will map each factor phi I into a cluster that contains the variables in phi I. So for instance, we have a factor here, phi A, and we need to map it to some cluster. And it can go like here, because here we mentioned variable A. It can go also here, or here, or here. We need to decide one of the factors that we will use. So in this case, we have associated with this factor here. So phi A, you're going to go to this factor that mentions variables A, D, F. We could go to another factor that's true. We could go here, for instance, that is true. We can do that. We just need to decide where the factors will go, and these will not interfere in the final results of the algorithm. In the same way, we have a factor here that is phi B that mentions variables B and A. So we need to find a place to put this, and we found it here. So we have here variables A and B, so we can place this factor B, phi B, in this node. And we continue to do that for all the nodes that we have, and also for all the evidence indicators. So if you have an evidence indicator for a variable X, we need to find a cluster that mentions variable X. That should not be difficult to do. We just look here and see which cluster mentions that variable, and we put the factor there. And we propagate the message into the Jointree between the clusters. And I'm going to use that idea of message passing. We will select one route, and first send a message towards the route, and the second pass away from the route, and we compute all the messages. And after passing 2 messages per edge in the Jointree, we can compute the marginals. They're going to be the probability of C and E for every cluster C. So the Jointree, and we haven't seen and discussed this before, it will be useful to answer multiple marginals, but those marginals must be over the variables in the clusters. So we will be able to answer something that is related to the probability, for instance, of D, F, and G. And it can be this, it can be D, F, and G, also some evidence that we set here. We can eliminate some variables from here and calculate, for instance, the probability of D, or the probability of D and F, or the probability of those variables and evidence, and so on. So, but we are restricted to the variables that are in the clusters. So let's take a look at one example that we can do it step by step to check if we are understanding everything correctly. So this example here, we're going to use linear chain Markov network. So we have it here. It's going to be this sequence A, B, C, D, and E, and we have the factors. And the factors are these pairwise factors that we see here. So it's going to be like this one, phi 1 of AB, phi 2 of BC, phi 3 of CD, phi 4 of DE. And we need a Jointree for that. And again, I'm going to assume that the Jointree is going to be given, and I'm going to see how to build one in the next lecture. So the Jointree is this guy here. It might be slightly strange to you, but these are the clusters. So cluster and cluster and cluster and cluster. And these are the separators, separator, separator, separator. And so I just represent the separators here as a box because I want to show the message going in each direction. So I need a little bit of space over there, so I represent it that way. So the first step is to associate the factors to the clusters. And we can do that any way we like, but here in this example, we don't have much space for changing anything. We need to put the phi 1 here, and the phi 2 here, and the phi 3 here, and the phi 4 here. Usually we use this big phi here to represent the multiplication of all the factors that go in the same cluster. In this case, we are just putting one factor in each cluster, so there is no multiplication at all. But sometimes we put two factors in the same cluster, we need to multiply them. Sometimes we put one factor and one evidence indicator, we need to multiply them as well. So in summary, this big phi here represents whatever we have, all the factors that when they're multiplied together, are going to be a resulting factor with all the factors multiplied. And the next step that is not absolutely necessary, we can just pass this, is to select one node as a root. And when we do that, just to organize things, we first send a message towards the root, and the second step we send message from the root to the other nodes. It's not absolutely necessary. We can organize the message passing without the ID of the root. We just need to be careful to send the message when we have received the message from all the other nodes. So we need to be a little careful about that. Otherwise, we can include the node into the implementation explicitly, and going to help to think about the problem, even though it's not absolutely necessary. And now we can start and send a message between the clusters. And we need to start, and a good way to start is look at these peripheral nodes like this node 1 or node 4, and because they don't need to wait for anyone to send message to them to start send the message. So we're going to start with node 1, cluster 1, send the message to the cluster 2. And what is the message? Remember that here we had a factor big phi 1, and we have variables a and b here, but the separator is just b. It means that we can eliminate the variable a, so we're going to eliminate the variable a and do this elimination over this factor big phi 1 here, and get the message to cluster 2. And when cluster 2 gets its message from cluster 1, it can send a message to cluster 3. And what's going to be this message? It's going to be a message in this direction here. It's going to be the message from 2 to 3. So we're going to use this notation. Remember that cluster 2 is defined over variables b and c, but the separator is just c. So we can eliminate the variable b. And this elimination will involve this factor here that we have, but not only this factor, but also the message that was multiplied. Remember when I send a message here, this message is multiplied by this factor here. So we have this guy multiplied by the message 1, 2. And if you are using the root, and we first send the message towards the root, and later on the message away from root. So in this case here, we will not send this message here, and we're going to wait for this message here to arrive first, and later on send this message, because this message here is going away from the root. But actually, technically, there is no issue, because as node 3, the cluster 3 has received this message to 3, it is allowed to send the message from 3 to 4. No issues at all. Actually, when you do that, we call this algorithm the forward algorithm. It's very popular in hidden Markov models like we saw. And there is also one algorithm that's called the backward algorithm. That's basically starting from the node 4 here and send the message in this opposite direction until the first cluster, the first node here. And it's also valid. But in this case, let me just erase this mess here. Let's use the root and respect this ordering here. So I'm gonna first send this message. So what's gonna be this message? It is the message that comes from 4 and goes to 3. It is composed by the factor that I have here, the big54, and with elimination of one variable that I'm almost forgetting about it. So here we have the variables de, but the separator is over d. So I'm gonna write here. I can eliminate the variable e over the phi4, and I start and send that message. Once the root receives the message from all the sides, it can now send the other messages away from the root. So in this case, can be like this message here and this message here. Let's just switch slides, otherwise we're going to lose here track things. So this is a little bit more organized way. So we have the message to 3, and have the message for 3, and now we can send the other messages. So the other messages will be, I guess the next one in my slide is going to be this one, that is the message 32, and it's going to be a summation. In this case here we have CD and C here, so we eliminated D. We're going to summation over D of the factor that I have here, that's the big phi3, the big phi3, multiplied by this message for 3 here. And I will be able to send this message here, that is the message from 2 to 1. Again, an elimination. In this case here, eliminate C. It's going to be the big phi for 2 times the message I got from this guy here, 3, 2. Let's again switch slides just to have a more clear view of this. So this is the message 3.2, and this is the message 2.1, and you can also make this message here in the next slide. So this is the message 3.4. Okay, now we have sent all the messages. We are complete. We are now in position to answer the queries. So we can pose queries involving the probability of A and B, the probability of B and C, the probability of C and D, and the probability of D and E. So these are the marginals that we can answer queries about. So you may be asking why this algorithm works, what's going on here that it making this algorithm compute the right thing. And the answer is actually what it's doing is taking the factors, multiplying and eliminating the variables, exactly as we did with variable elimination. So just to think about one example, let's suppose that we want to compute this marginal over C and D. So it's going to be the probability of C and D, right? We also call this the belief of C and D. It's another notation, so we are using it here, the belief for the cluster 3, C and D. And what is inside this at the end of the computation? So what we have here is basically we have this big phi3 that was the factors associated here. So we have this big phi3, and we're going to multiply by the message that we received from the neighbors. So we're going to be this message here, 2, 3, and also multiply by this message here, 4, 3. That is exactly what we have in this node here at the end of the message passing. And if we detail this a little bit more, and we open all those equations. So we have this guy here. That is actually what we wrote here. But we can use here, instead of mentioning the message 2, 3, we can actually put this small equation here. So we're gonna move it to here, and also we're gonna replace this message 4, 3 by its variable elimination of E here. And again, we are mentioning message 1, 2. We can replace it by this summation here and placing it here. So when we look at this final equation, so what we have the factors that were mentioned, variable C and D, that is this big phi 3 here, and it's going to be multiplied by, first, we have the factor phi 1. So the phi 1 was here, and when I send it to here, I eliminated the variable A. And it's good about eliminating the variable A because none of the other factors mention this variable A. At the same time, I'm not interested in variable A because I'm answering queries regarding the marginal C and D. That's all good. So when we look at this part here, we're saying that we're going to take this result and multiply by the factor that we have here, this big phi 2 here, but I will eliminate the variable B in this process. Again, I'm fine with that because we don't have a variable B in this side here of the graph. I'm not interested in variable B, I'm just interested in variable C and D, so I can eliminate that. And it will also multiply by the factor 4 that I had here with the elimination of variable E. There is another variable that I'm not interested. So see that we are multiplying things in the correct way. I'm not eliminating variables D and C, even though they were present here, and C was present in this cluster 2, D was present in the cluster 4. I did not touch those variables. I did not try to eliminate them. I multiplied them and moved that to the cluster 3. So exactly what we would have if you were using variable elimination. So let's take a look at another example now with Bayesian network. So in the previous one we used a simple Markov network. Let's take a look now in a larger Bayesian network. So this is the Bayesian network. This is the modalized graph. So we transformed the Bayesian network into an undirected graph. These are the factors that we have. So we have phi C for this guy here, phi I for this guy here, for CD for actually this guy here, GDI for this guy here, IS for this guy, LG for this guy, JLS for this guy here, and HGI for this guy here. So we have one factor for each of the nodes. We need to find a Jointree that you don't know how to do it, but they're going to be given to us, and associate those factors into the Jointree clusters. Next slide. So let's suppose that this is our Jointree. So it's a large one, it's still a sequence of nodes. Yeah, it's common, but remember that if you have a sequence like this, it's going to be a tree, so no issues, but it doesn't need to be a sequence. The Jointree is not the case that it's going to be always a sequence like this. It's going to be a tree, so no cycles, but it doesn't need to be a sequence. So we associate the nodes, so I can associate C here, I can put it here, I could put I over there too if I want, CD over here, and so on. So we distribute the factors over the clusters, and we start in the process of sending the messages. So this is the Jointree with the message. For each edge, we need to send messages into two directions. So we have the message from left to right and right to left. We need to be very careful. In this case, we are not choosing a root node. We are just sending the message in the two directions. But when we do that, we need to be very careful. So for instance, what is a common mistake that people do when they are implementing this algorithm for the first time. For instance, we need to start from somewhere, and usually we start from this node or this node. These are peripheral nodes that we don't need to wait for anyone to send us a message in order to start. So let's suppose that we send the first message going to be like message 1, 2. So we send this message here, right? When the cluster 2 receives this message, it's going to be in position to send the message to the cluster 3. But it's not yet in position to send this message here from 2 to 1. Because in order to send this message, I need to receive a message from the node 3. Take a look on here. That's the definition of the message from 2 to 1. It doesn't mention the message from 1 to 2. It just mentioned the message from 3 to 2, that is this message here. So in order to have the message from 2 to 1, I need the message that came from 3 to 2. And I do not use this message from 1 to 2 here, right? So it's a very common mistake that people do is send a message from 1 to 2, and once you have received the message from 1, I send a message to 3, and I also send a message back to 1. And that is not good, because the message that goes to 1 does not use the message that we got from 1. So that's a very important detail about the implementation of this algorithm here. So I guess that's good for this video. Let's take a break, and we're going to continue in this same subject, but now we're going to talk about answering queries and setting evidence for the Jointree algorithm. So see you soon.